Okay, we're back to chapter 5 again. This is turning out to be quite a large module. That's why in a normal course it takes several weeks to accomplish. But we are not done yet, but we're getting closer. So let's get started with hydroboration oxidation. Okay. Hydroboration oxidation is a two-step sequence. So the first step is going to be a hydroboration. The second step is oxidation. Now notice on my arrow, I have a 1 and a 2. So this is the first step, which is the hydroboration. And this is the second step, which is the oxidation. The net result then is making an alcohol. So this is another way to make an alcohol. And this actually gives the opposite regiochemistry from before. So what I get is an anti-Markovnikov hydration. So in this one, the hydrogen adds to the more substituted carbon, and the OH adds to the less substituted carbon. So this is the opposite of what we achieved when we did acid catalyzed hydration. Remember, it was very difficult to make primary alcohols, but I can do this because my hydrogen actually ends up here and my OH ends up on my least substituted carbon. Again, this is the opposite of what we've seen before. So it's called anti-Markovnikov hydration. So the first step is the addition of borane to an alkene. And this happens sequentially. What I end up is the addition of 3 alkyl groups to that boron. So that's called a trialkyl borane. So I have 1 addition, 2 addition, 3 additions, and I end up with that trialkyl borane. Now, borane is most commonly used as a solution of borane and tetrahydrofuran. So this is sort of how you're going to see it written a lot. But basically, you could also see something like that as well. This would be called borane tetrahydro or borane tetrahydrofuran etherate. And I do have this sort of a positive negative thing going on here, but I just want you to know, instead of the specifics, just that when you see this reagent here, or if you see BH3, you're thinking about boration, like hydroboration. I'm adding a boron. Boron is atomic number 5. Remember, boron has 3 electrons in its valence shell, and it was an exception to the octet rule. Remember, it only formed 3 bonds, and it was electron deficient. Now, it's sp2 hybridized. So that boron is sp2 hybridized. And I have this empty p orbital that's available. So this is actually a Lewis acid. So because of this empty p orbital, my trivalent species are actually electrophiles. Remember, this is electron deficient. I do not have an octet. So that empty p orbital allows it to accept electrons and then sort of make it even more electrophilic. Hydroboration is regioselective. Remember, it's anti-Markovnikov. So when I think about the regioselectivity, right? Oops, I wanted my pretty yellow pen. When I think about the regioselectivity, hydrogen is adding to the more substituted carbon, and then the boron adds to the less substituted carbon. I also have to consider stereoselectivity because this is syn. So these add to the same face of the double bond. If they're cyclic, notice I will get a cis. Now I want the red. I will get a cis configuration here, right? This is the cis isomer. And it doesn't matter, I get both. I get an enantiomeric mixture if they're chiral, because it could add to the top or the bottom face of that thing. But if I have a cyclic structure, what I'm going to get is the syn addition. Now I'm just going to go over this quick. This is one of this is one of the reactions that I'm really not going to focus on the chemist or on the mechanism. So you're not responsible for this. Just know that this difference in regioselectivity, that anti-Markovnikov, and the syn stereochemistry can be attributed by this four-membered cyclic transition state. So regiochemistry is because I formed this four-membered cyclic transition state. There are two possible transition states. I have some carbocation character, but this one is going to be lower in energy. So this is favored. And notice that if I look at where my center of positive charge or my partial positive charge is, this is on the more stable, it's not a total carbocation, but it is partially positive. So that's the more stable position. This is kind of like a primary, whereas this is like a secondary. So the hydrogen is going to add here, and the boron will add to that least substituted carbon. Now the syn is due to steric factors, and we'll talk about that later. Oh, I guess we won't because we're moving on. The syn is because when these are larger groups, they want to be away from those alkyl groups. They want to be surrounded by fewer carbon atoms, which is actually why you would get the boron adding to the least substituted carbon. All right, let's talk about hydrogenation. Now, remember, hydrogenation. This is the addition of hydrogen. If you can tell, these names give us a lot of information on what is actually happening. That's, of course, by design. This is a reduction. Remember, if I add hydrogen to a species, that is one of the criteria for reduction. So what happens is I add hydrogen to alkenes or alkynes. This is a symmetric reagent. So I have no regiochemistry. I do have stereochemistry though. And my stereochemistry is syn. So if I had a situation where I had a cyclic structure and there was a difference between the hydrogens being syn or anti, I would get the syn. So basically what I need is some sort of catalyst, and this is usually nickel, palladium, or platinum. It's a metal catalyst, and what I get is the alkane. So I add hydrogen to both sides of my double bond. I get a fully saturated alkane when I do this. Notice if I have an alkyne, to get the fully saturated alkane, I have to add 2 equivalents of hydrogen because there's 2 pi bonds that actually have to be added. So I have to add 2 molecules of hydrogen. I'm adding 4 hydrogens to that double or the triple bond in order to get to that alkane, that fully saturated molecule. So this process is used commercially to convert unsaturated vegetable oils to saturated fats. So if something says it's hydrogenated or partially hydrogenated, what I'm going to do is take double bonds in my fats, which are actually healthier. Polyunsaturated fats from plants are healthier. And then we chemically make them non-healthy because we're saturating those double bonds. So that's actually not a great method. Those margarines and cooking fats have some stability benefits. I mean, I think you can keep margarine around for forever, or just like those cooking fats too. I don't know, my grandmother used to cook with lard, which is probably one of the most disgusting things I've ever seen, if anybody knows what I'm talking about. It's just like white fat in a jar. It's pretty gross. Now, this process creates trans fatty acids or trans fats, which also are not very healthy for you. So this has come under intense scrutiny in recent years. Now, alkenes will react with these hydrogen to give alkanes. Again, I told you the most commonly used metal catalysts are platinum, palladium, and nickel. I can also, because I need that metal, it's called catalytic reduction or catalytic hydrogenation. When I take a structure like cyclohexene, I'm adding hydrogen to it, and then I get the fully saturated cyclohexane. The most common pattern is going to be the syn addition of hydrogens, which means that both hydrogens are going to add to the same face of the double bond. So catalytic reduction is predominantly syn stereoselective. So that means something, especially if I have a cyclic structure that has substituents. So if I add hydrogen to this and it adds syn, what I'm going to get is the cis products. Notice I get 70 to 85% of that. Because what I just did, right, is if I have those CH3s, I also have the hydrogens on the same side. So this, with the hydrogens on the same side of the ring, that's syn. This would be an anti-addition, and notice that we really don't see that. So predominantly I have syn stereoselectivity in catalytic hydrogenation. Now, the reason that that occurs is because I actually have a transition metal catalyst. So what happens is the hydrogen and the alkene are absorbed on the catalyst. One hydrogen is transferred and I form that new CH bond. And then the second hydrogen is transferred and the alkane is released. So when you think about this, I'm forming this bond here, and then I form this next bond. And it's on the same side because of that absorption onto that metal surface. Now I can tell how hydrogenation, what kind of double bond is more stable than any other kind of double bond by something called the heats of hydrogenation. So if you notice, simple ethylene, this is a, when I hydrogenate something, this is an exothermic process. So ethylene, where I just have hydrogens on the double bond, gives us a negative 137 kilojoules per mole. The other number is kcal per mole. If I have a substituent, notice this drops down to 126. Here I also have one substituent and it's about the same magnitude. Now I have two substituents, one on each carbon, and it drops down a little further. I have the trans, which is actually a little lower, which means the trans is more stable than cis. The lower the number, the more stable that alkene was, because the less energy is actually given off when it goes to the alkane. Notice if I have three substituents, that drops further. And if I have a tetrasubstituted alkene, that would be the more stable. So this is the most stable alkene, which is tetrasubstituted. And then this is the least stable, which is unsubstituted. And based on this result, I can find an order of stability in my alkenes, whether they're monosubstituted, trisubstituted, or disubstituted, or tetrasubstituted. I have a tickle today. So the reduction involves the net conversion of a weaker pi bond to a stronger sigma bond. The greater the degree, this is what we were just talking about, the greater the degree of substitution of the double bond, the lower its heat of hydrogenation. So what that means is the greater the degree of substitution, the more stable the double bond is. So you can tell that that transalkene has a heat of hydrogenation that's lower, so it is more stable than the cis. The trans is more stable than the cis, which makes sense because remember we talked about how the trans has less steric encumbrance. If I have something that's trans, my R groups are farther apart for each other, and if I have something that's cis, I can have that interaction there. Right? So that difference is due to that non-bonded interaction strain, that steric strain in the cis alkane. So I can actually look at this, and if you look at the delta H, which is really the enthalpy, the energy, the trans is more stable than the cis by 4.2 kilojoules per mole, right? This is bringing the alkyl groups of the alkene closer, where I have a much larger increase in steric strain. But notice it's not that huge. 4.2 kilojoules per mole is significant in the world of chemistry, but what happens here is the higher heat of hydrogenation means that more heat is released, and indicates that alkene starts at a higher energy level, which means overall it's going to be less stable. If I'm lower on my energy diagram, then I'm a more stable compound. So I can tell stability of alkenes by using these heats of hydrogenation. Okay, one more topic in this chapter, which is the reaction of alkenes. Remember, we talked about alkynes in chapter 4. And one of the things we talked about and we sort of referred to in chapter 2 again is that terminal alkynes are weak acids. And remember, if you go through the areo, that sp orbital is closer to the nucleus and gives us a more stable conjugate base. So if I look at this, right, my pKa for an alkyne is much lower than my pKa for an alkane, and then my double bond is somewhere in between. I mean, this is a logarithmic scale, so remember that these units are really significant because that's orders of magnitude greater. Notice it's nowhere near what we consider acidic, like HCl or H2SO4. But in the organic world, what we really have to focus on is that I can actually do chemistry with the conjugate base. I make a carbanion, which allows me to use that carbanion as a nucleophile, which can do chemistry with other types of molecules, and I can build my carbon skeleton by forming new carbon-carbon bonds, which is really important. So what this is an alkylation. This is what it's really used for. I can alkylate my terminal alkyne. So if I think about how I want to do this, so I want, the net result is, I want to form this carbanion. And then I'm going to have something. This is some alkyl group. And then this is some leaving group. And this is going to attach to that carbon and kick out that X. And what I'm going to get is a new bond that forms to the carbon of that alkyl group. So I just increased the carbon numbers in my carbon skeleton. I made a carbon-carbon bond, which is awesome in organic synthesis. But I have to use a really, really strong base. If I look on this slide, what I notice is that if I use sodium hydroxide or potassium hydroxide or anything that has a hydroxide as the base, the pKa of water, which is going to be the conjugate acid of hydroxide, is much lower. So this is the stronger side. So my equilibrium is actually going to go in that direction. And I do not form this. I don't form this carbanion, this acetylide anion. So hydroxide doesn't work in order to make this acetylide anion. What I need is something really stronger like NaNH2. If I look at NaNH2, I'm going to find out that ammonia has a much higher pKa than 25. So if I use NaNH2, my this is going to be the weak side, and then I can form that acetylide anion. So this is both a strong base and a nucleophile. As a nucleophile, it can donate that lone pair of electrons to some electrophilic carbon atom. So this is electrophilic because I have the partial positive, partial minus due to that dipole because of the increased electronegativity of the chlorine. So this is an alkyl chloride. And notice my negative charge, my electrons are going to attack that electrophile and kick out that chlorine. So this is that new carbon-carbon bond. And what I end up with is just sodium chloride. It's really important that I form this new carbon-carbon bond. Because the alkyl group is added, right? I just added an alkyl, which is this methyl. So the methyl is from this piece right here. It's called alkylation. So if I alkylate an acetylide anion, I'm adding an alkyl group, which means I'm basically reacting it with some sort of an alkyl halide. Now, the importance of acetylide anions in synthesis is large. Anytime I can create carbon-carbon bonds and build up the complexity of my carbon skeleton, that's going to be a win-win in synthesis. I mean, when I think about synthesis in organic chemistry, I'm thinking about making really large molecules. And I'm doing this from compounds that are very simplistic. So I'm building my molecule from lower carbon count reagents. And so I need ways that I can introduce carbon-carbon bonds. And this is one of the first ways that we can do this. Notice in all of the alkene reactions that we've discussed thus far, introducing functionality. I make an alcohol. I can make an alkyl chloride or an alkyl bromide. I can make, I reduce functionality. I go from an alkene to an alkane. But what I didn't do is make a carbon-carbon bond. So anytime I can create a larger carbon skeleton, that's something that I really want to invest in. So here's sort of a sequence to describe what I'm talking about. So this is going to pull off the proton to make the acetylide anion. And then now I'm alkylating with a 2-carbon ethyl group, right? So this is the piece that's going to get put on here, and I form this new carbon-carbon bond. I can do this sequence again, right? I can do another alkylation. So this is a second alkylation. And now I'm using propyl bromide. So now on this side, I'm putting on a 3-carbon chain. So I went from 2 carbons to 1, 2, 3, 4, 5, 6, 7 carbons. I added 5 more carbons. Now, this alkylation is generally only successful for methyl and primary alkyl halides, and there's reasons for this that we're going to talk about next. But for now, just think of the fact that I have just learned a whole bunch of reactions in organic chemistry in this chapter. We have ways to introduce functional groups in my addition to alkenes, and now we have ways to make carbon-carbon bonds in my alkylation of acetylide anions. Alkynes can also reduce with hydrogen, as we've seen in when I introduced hydrogen. So if I treat an alkyne with H2, and again, I need my transition metal catalyst, I can use 2 moles of hydrogen and go down to the fully saturated alkane. Now it's very hard. I mean, if I have enough hydrogen, this is going to go. Obviously, the first thing that happens is I go either the cis or the trans alkene, right? So I have 1 molecule of hydrogen to do that, and then 1 molecule of hydrogen to take it all the way down. 3 atmospheres, this is pressure, and that's significant. I mean, you have to do that in a special apparatus that can allow your compound to, or your apparatus that can withstand some pressure. But what I got is 4 additions of hydrogens along that triple bond, and I get the fully saturated butane. Now, I can choose a different catalyst and stop the reaction at addition of 1 mole, right? So if I choose a proper catalyst, I can stop the addition at 1 mole of hydrogen, and this is going to make an alkene. So I can stop after I add 1 mole of hydrogen and I get the alkene. Now, the most commonly used catalyst is something called Lindlar's catalyst, which is a finely powdered palladium metal, which is deposited on solid calcium carbonate, and it's modified with lead salt. I'm not going to give you the formula, the structures, anything. Just know Lindlar. Look at here. When I want to use that reagent in the synthesis, I just put Lindlar catalyst. This is called a poisoned catalyst. What that means is it's less reactive. So it allows me to stop at that double bond. If I go through one of these, I can't stop at the double bond. I can't just use one equivalent of hydrogen and stop at the double bond. I'm going to get triple bond, double bond, and alkanes because it's very reactive. So to use regular catalytic hydrogenation, it's a great way of making the alkanes from the alkyne. But if I want to make the alkene from the alkyne, then I'm going to have to use the Lindlar catalyst. Now there's something else that's really important. This reaction with Lindlar catalyst is cis stereoselective. So I get a cis alkene. I always get a cis alkene. My 2 alkyl groups that were attached to the triple bond are now going to be cis to one another. So this is going to be syn stereoselectivity. The hydrogens are added from, remember, the hydrogens are added from the same face. So they are on the same side of that double bond. So I get cis alkene here. Okay. I'm going to leave you here. This is something that you should know. Figure out how to start with acetylene, which is just my simplest triple bond, and then using all the reactions and all the reagents that we used in this reaction, propose a synthesis for each of the following compounds. Any compound that is made in one part of the problem may be used as a starting material. I'm going to do the first one. Let's say I have acetylene. And think about this. I want to go to 1-butyne. So 1-butyne is this. So notice I replaced this hydrogen with a CH2CH3. Well, there's only one way to do that. I'm going to take step 1, form the acetylide anion with NaNH2, and then I'm going to use an alkyl halide that has 2 carbons. So if I do that, I'm going to end up making the anion and then alkylating, and I end up with that. Now, let's say, notice here, any compound made previously can be used as a starting material. So now I want to be able to go to 1-butene. So this is a double bond. So is there a way I can go from that alkyne to the double bond? Yes. I'm going to use hydrogen in the presence of Lindlar catalyst. Now, I don't have to worry about stereochemistry here because I don't care what that stereochemistry is. I don't have cis or trans. but I need to be able to stop at the alkene. So in order to stop at the alkene, I need to use Lindlar catalyst. I'll do one more. What if I wanted, actually I'll do two more. What if I want to go to make 2-butanol? Well, or 1-butanol. 1-butanol is this, HO, CH2, 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 CH3, right? So this is a primary alcohol. So what if I do hydroboration and then oxidation, which is NaOH, H2O2, and I end up with that alcohol? Well, this is anti-Markovnikov because this is the least substituted carbon that my OH ends up on. So I have to use hydroboration. What if I wanted to go to 2-butanol? That's this guy. So that can just be water and acid, right? So this is going to be Markovnikov addition because my OH ended on the least substituted carbon. So that would be Markovnikov. Notice if I want to get the primary alcohol, I'm going to use the anti-Markovnikov conditions, which is hydroboration, oxidation. If I want to get the Markovnikov addition, where my carbon, and I actually end up with a secondary alcohol, I'm just going to use a regular acid catalyzed hydration. So this is what I want you to think about. I gave you a good start. Now see if you can figure out ways to continue what we were doing and make these other compounds from what I have on this paper here. You can use these different products as intermediates. And this is something that I might give you on a test. You have to be sort of familiar with these reactions, and you have to know the regiochemistry when it's applicable. You have to know the stereochemistry when that's applicable, especially in cycloalkane or cycloalkene systems. And there's a lot of things you have to know. But this sort of is the higher level of cognitive ability, trying to create these molecules from simple things. You have to know your reactions really well in order to really understand this and get this. So practice. We will have a Zoom session in the next week. And if you don't know how to do this, I suggest you try to attend the Zoom and then ask questions about the synthesis, because this kind of skill, honestly, this isn't that complicated. If you were to go into organic 1 or organic 2, you're going to notice that this is just the tip of the iceberg. But it's enough for our class. Our class is a basic class, so we're not going to go into too much depth. But what's on this slide, where I can take a couple of simple things and make more complicated molecules. And remember, I'm using all of the reactions in this chapter. These are the reactions that we've learned, and I can do a lot with these reactions. So we are well on our way at this point to becoming very sophisticated organic chemists. So with that, I will leave you to your studies. We are now done with chapter 5, and then we are moving into chapter 7, which we start looking at substitution and elimination reactions. which basically are the reactions of alkyl halides. So good night.